Okay, computational finance is very useful when you want to make evaluation of some more complex financial instruments. If you attend corporate finance course, you know that corporations basically on their passive side have their own capital or the capital that belongs to their owners, so it's called just equity, and external financing, it's usually just interest-bearing debt. So you are focused on debt financing, on equity financing, and what we started with on computational finance is we learned some very basic simple tools of how to model the behavior of interest rate needed for valuation of debt. So we use an example of Wasilewski model. We also learned geometric Brownian motion that is used for simulation of logarithmic rate of returns and hence also prices of equity. So we have like tools to work on these basic instruments available for investors in economy. But of course we know that there are more complex financial instruments available, and usually by more complex we mean the derivative instruments, so instruments that uses some other instruments for evaluation purposes. And on computational finance we'll focus on option valuations. So you of course, I assume, understand very well what an option is. We start with the simplest contracts on option, call on equity. We have some exercise price that we will use. We have other assumptions regarding or needed in order to make evaluation of this option, and we'll start with valuation in most famous, most well known, and one of the simplest model. So it would be Black-Scholes-Merton model. And as usual on computational finance on this course, we will just try to apply some methods that are available, are well tested in we'll try to apply them in a Microsoft Excel and later on in Visual Basic environment. So let's just start with applying these formulas that we can find for a Black-Scholes model, Black-Scholes option valuation model, and that we have it here. So our first formula is the formula that we will use to value call on equity option. So basically our contract where investor has the right to purchase underlying instrument, so instrument that has a price of S for an exercise price equal to 95. Current price of this instrument is 100, so this equity currently costs 100, and we need to wait 6 months until the maturity of the contract. So in 6 months our investor will be able to purchase this instrument for 95. We have interest rate, risk-free interest rate equal to 5%, and we also know about the dividend yield that this instrument is paying, this underlying instrument. So dividend yield is just dividend paid by the company per price of a share. So this company is paying on a continuous basis. These are all assumptions about on a continuous basis 2% of dividend. The volatility of underlying instrument is 20%. In order to calculate the price of a call option, we need to start with checking assumptions and checking current values. So what we want to know is the current price, so this is equal to 100. Then we have this base of natural logarithm minus q, so this is discounting with the dividend yield. Please note that if you have a position in underlying instruments, you are allowed to, or you have the right to receive this dividend. If you have an exposure with a derivative instrument with options, you don't have this right. So you need to incorporate this discounting or dividend yield you want received into the price of your instrument. You won't get the dividend. And then you multiply by this ND1. We will get back to this ND1. And after we have this first part, so underlying instrument discounted with dividend yield times something, and this N is normal distribution, so times normal distribution with some D1. Then we subtract, and what do we subtract? We subtract exercise price that we know, that is known as 95 in this contract. Then we have again base of natural logarithm and some, so this is some discounting, so we use interest rate, risk-free interest rate for continuous discounting, and again times something from normal distribution. This time we have D2. Okay, let's try to calculate this ND1 and ND2 and also other discount factors. Okay, so let's calculate D1 at the beginning. So this D1 is equal to what? And I have now my initial relationship between share price and exercise price, so initial ratio. And to this initial ratio that I can observe on the market in terms of this contract, I have to add, what do I have? I have interest rate that I will get, interest risk-free rate, minus dividend yield that I won't receive. So it's a kind of like feature or characteristic of a derivative instrument. If you have direct exposure to underlying, you will get the dividend. If you have this exposure via derivative instrument, you don't have a right. So only as a shareholder you have the right to get this dividend. So we have interest rate, we have dividend, all in per annum values, and I have also half of my variance, 0.5 times my volatility, raised to the second power, or is per annum, so I need to scale it down by option maturity. With option maturity, have my numerator, and I need to what? I need to standardize it with standard deviation. So my standard deviation is 20%, but if I want to scale it down for option life, I need to use square root. So this is, I need to use square root because this is standard deviation, not a variance. So my D1 is 0.53 and my ND1 will be normal cumulative distribution. So you use normal distribution function for this D1 and use true optional, true additional or second input, so for a cumulative distribution function. So it's 0.7. Let me check if everything is correct. It looks okay. And in case of D2, the only difference is in the sign that you use for half of variance. So if you copy the formula here and paste it for D2 and change the sign, you will have the proper value, and the same for normal standard distribution and true. Okay, so it's 0.65, 0.7. Now discount factors for this. So I have discount factor for interest rate or risk-free rate available in this model. I need to scale it down for half of a year. So this is more interest rate, and second yield is the yield that you get if you're a shareholder. So it's dividend yield, 2% times option life again. And I have ND1, ND2, and I have discount factors for yields. So I have all inputs I need to use for my call option valuation in Black-Scholes model. So let's put it on together and calculate price of an option according to this model. So I have a share price. I'm using this discount factor for a dividend yield. I want to receive a dividend, and I'm using this ND1, which is like kind of like discount factor, also not different. And I subtract exercise price that I'm like allowed to use as a purchase price if the contract expires in half year. This would be in half year, so I need to discount it to present value terms, and I need also to use this adjustment for probability, kind of like probability adjustment. Okay, so this is the price according to Black-Scholes model. So if you remember this formula, it's may be difficult or may seem difficult at the beginning to memorize this formula, but actually if you put this into individual elements and think of them, it's becoming quite easy. You subtract share price of an instrument from an exercise price. So this is basically your payoff formula when the contract expires. It's share price on the market minus the exercise price that you have in your contract, right? So if the difference is positive, then you are in the money, so you exercise the option. So if this situation will still be in like half year when the option matures, so if the price won't change or at least be again equal to 100 when the contract expires, so your payoff would be just equal to this difference, right? Then but you are half year later, a half year before this contract expires, so contract expires half year later, so you need to use this time value of money concept to somehow incorporate this into valuation. So of course you are familiar with simple time value of money, so you can just use interest rate for discounting. You also, it also I believe maybe kind of intuitive to use the discount for dividend yield. So dividend yield is something that you want to receive, so just please take it out of your model, take it out of your valuation with this discount factor. Like the more challenging to understand is this ND1 and ND2. And like from our perspective, you don't have to like understand this. It's not that important actually. A lot of people like don't think of what ND1 and ND2 is. You can just use this, trust the formula and use it in practice. If you're interested in getting some intuition about, at least intuition about ND1 and ND2, I am uploading understanding ND1 and ND2. I like this paper very much. It's very short, just a brief introduction, so I encourage you to read this. Just a brief introduction, because maybe it will be more intuitive after you read this paper. So I start here at Black-Scholes probability assumption at page number 13. So what I would like to notice here is that in Black-Scholes model we have this underlying instrument ST at time t, and we know that price follows log normal distribution. So if you have a logarithm of this price, this logarithm of a price follows normal distribution according to this formula, and you may be already familiar with this part. So we have this me minus half of the variance raised to the second power. Precise interpretation, so this would be our volatility. What is this interpretation of our mean? And again, I encourage you to read this. If we have expected return relative, and so price at some time t over current price, so this like mean long level of prices that follows log normal distribution, is this our mean return? this assumption of a drift, because use this value for a drift. And also, if we have logarithms of a price, if we use them to calculate rate of returns, this rate of returns will follow normal distribution with this value. So this mean minus half of the variance squared. So this is something that you may already recognize from our D1 and D2 formulas in Black-Scholes, and also something that you can remember from our geometric Brownian motion. So this is our geometric Brownian motion that we had introduced on our labs, on our classes. We have logarithmic rate of returns. It's equal to this mi parameter minus half of the volatility squared. And this is something that we also use in Black-Scholes formula. So this is this risk neutral valuation. We don't have this, we don't have this. So this risk neutral valuation, it makes more even easy to get this D2 part. So in D2 part, you actually assume that you have some initial space, initial room, or initial return where your share price and exercise price serve as these factors. So if you calculate logarithm of share price and exercise price current, you may think of this initial 5% rate of return that are like incorporated into terms and conditions of this price. So you like start with this 5%. You start with this 5%. So if this is when contract expires, so if at expiration of a contract you have price equal to 100 over current 95, your return then would be equal to this, in continuous terms, slightly more than 5%. So it's like already given, built into terms and condition of contract. You purchase a contract when current share price is higher than exercise price. So option is currently in money. And then you add something, and what you add is this rate of return that you expect to realize. So this is your risk neutral rate of return. You will get interest rate, risk-free interest rate available on the market. You won't get dividend yield, so you like need to pay the dividend yield, but on the other hand you get this price of money, so risk-free interest rate, but you need to subtract half of the volatility squared, and you subtract half of this volatility squared because of this risk neutrality assumptions and because of the fact that rate of returns follow normal distribution. And if shares follow log normal distribution, then this means for log normal distribution you have to subtract half of this volatility squared. So this ND2, you start with this 5%, and if you have positive interest rate that is higher than a dividend yield, then you expect it also, if the volatility is not like abnormally high on this market, like super high, then you expect also this positive drift that is like present in economy, present also for this underlying stock, to increase this initial rate of 5%. It comes at the price of volatility though, so you may actually end out of money, but you expect your rate to be higher than 5%, and this is why this option costs you more than this initial 5. This option costs you 9. In the denominator, you just standardize this with standard deviation, like a normal standardization process. So you have initial gain plus something that you expect. So from understanding this point of view, from point of view of understanding this ND1 and ND2, the second factor, so D1, is like risk-adjusted probability of exercise price. So you expect this 95 to behave according to this trend, this shift in our economy. D1 is more difficult to understand, but basically it's like contingent receipt from your difference. So it's like price of this exercise, given that it has end up in the money. So it's like a bit more difficult, but for D2 simpler, what you expect to happen with assumptions. So if we use geometric Brownian motion, we use this formula or a similar formula to model the behavior, and with these assumptions it will generate positive rate of return that we add to this initial ratio. In D1, D1 is like contingent on the fact that that we end up in the money. So there, I believe, also some YouTube, or there used to be some YouTube movies on the intuition of Black-Scholes model, but this summary from the paper that I'm uploading, I find it very, very useful. Again, you don't have to like know this is only like optional thing if you want to have a bit more understanding. Thank you very much.